Okay, so it's time now to take a look at the roses. Those are a little harder. I think the cosine roses are a little bit more simple than the sines, but I'll hopefully make this make sense here pretty quickly. So let's jump in. We'll do 2 cosine roses and 2 sine roses. We'll play again with the even versus odd values and how that actually plays. So let's just jump right on in here. And so what I'm going to do is for the cosines, I'm just going to really leverage what I would like to do. So I often will use this idea of what I would like to do. And what I want to do for theta on a normal cosine is I would love to use these theta values. I just like to use 0, maybe pi over 3 and pi over 2. So those are really simple values to give me what I would like to see happen. But what you want to remember is by graphing by transformation is anytime this thing happens. Now, of course, normally if it was just 10 cosine theta, we would have, the cosine of theta would be, the cosine of 0 is 1 and we'd get 10. The cosine of pi over 3 is a half, so we'd get 5. And the cosine of pi over 2 is 0, so I'd get 0. But what happens in graphing by transformation is some weird things happen. And that is when you say you're going to multiply by theta, ultimately what it does is it divides by theta. So these theta values all get divided by 3. So 0 divided by 3 is still 0. Pi over 3 divided by 3 is pi over 9. And pi over 2 divided by 3 is pi over 6. And as it turns out, the results of those divisions are the same. Now you could check it out because pi over 9 times 3 is pi over 3. The cosine of that, pi over 3 is a half, and I get 10. So anyway, this is kind of what happens. I'm just going to graph these 3 values, and then we're just going to use some really strong symmetry arguments to finish our story. So at angle 0, I have a radius out here at 10. By the time I reach pi over 9, and I'm going to have to estimate just a little bit where pi over 9 is, but it's somewhere in here. So by the time I reach pi over 9, I'm down to a radius of 5, and by the time I reach pi over 6, I'm at a radius, pi over 6 right here, I'm at a radius of 0. So that's kind of what I have. Now, this is why this is such a strong argument, is that I know that not only does this cosine have x-axis symmetry, which is going to allow me to take this point and put it down here and therefore complete my petal. I also know that because 2 pi represents the entire circle, and this thing has 3 petals, that there will be a petal space perfectly every 2 pi over 3. So I have a rose that has a tip at 0. So if I rotated 2 pi over 3 and I rotate an additional 2 pi over 3, I'm going to continually get these little roses that are centered at these values every 2 pi over 3. And so sometimes what I will do is I will just come in here and I'll just kind of estimate about how fat they were and then just kind of copy them. Now, again, you don't have to do this part about the estimation of the width, but I found it to be helpful to make them look better. And so we now are done. And so literally all I really did is I plotted 3 values, this one, and this one, and then I used symmetry. Now, of course, Desmos does a far better job because they use hundreds of points instead of 3, but this is their graph. And you'll notice that theirs is a little smoother than mine, but it's all right. And you'll notice that this has a leaf right here at the origin because you take 10, 0, but if you divide by anything, 0 by anything, you keep 0. So on my second one, I decided to go a little harder. And so this time we're going to go to 4 theta again. What I would like to do is use 0. So again, this is assuming it was just cosine theta. The radius would start at 8. By the time I reach pi over 3, it would be down to half. And by the time I reach pi over 2, it would be down to 0. Again, but what I have to use is this. So again, all of my thetas are being divided by 4. So 0 over 4, pi over 3 over 4 is pi over 12, pi over 2 over 4 is pi over 8. That's going to still result in the same radii that we saw a moment ago. So at the angle 0, I'm going to 5, 6, 7, 8 right there. there's A. By the time I reach pi over 12, which nicely is this guy right here, it's dipped in to be a radius of 4. And by the time it reaches pi over 8 in here, it's 0. Now we're going to go ahead and just use our symmetry and grab that data value. And then we have an extra little piece that, since this 2 pi represents the entire circle, and remember, when there's an even value, it doubles, so there should be 8 petals. So there's going to be a petal every 2 pi over 8, or pi over 4, if we reduce that. So my first petal right here is at 0. My next petal is at pi over 4, so it's going to be right here. My next petal is at 2 pi over 4, right here. My next petal is, so 8 at 2 pi, 8 at pi over 4, 8 at pi over 2, which is 2 pi over 4, 8 at 3 pi over 4, 8 at 5, 6, 7, 8, 8 at pi, also known as 4 pi over 4, 8 at 5 pi over 4, 6, 7, 8. Does take a little bit of time to do these, especially when you have so many. But then the nice thing is we just know that they have this kind of general shape. And so I could kind of just try my best. Again, this one is going to be one of my poorer examples because I did probably, oh, that's terribly thin. Don't do that. That was terrible. But honestly, if this is what your graphs look like, I'd actually be okay with that. There's not a lot of room in here, it appears, because by the time you pack all 8 of those petals in, you've got a lot of information. But what's cool about that is all of that was derived from literally 3 points. Now, the reality is what Desmos does is it's sitting right there. Again, notice 8. There's pi over 4, 2 pi over 4, 3 pi over 4, 4, 5, 6, 7 pi over 4. They're all sitting right there. I guess maybe my petals were a little bit too wide, but you know, it is what it is. So there's my pi over 12 at 4. 1, 2, 3, 4 right there. I just probably came out a little fatter than I should have on that first petal. So now, this is the one I got to slow down on because the sign is a little bit harder. So again, let me go back to that idea of what I would like to do and what I can do. So what I would love to do for a sign is I would like to start at 0, which of course is 0. I'd love to use pi over 6 where its radius is a half. That's going to give me 5. And I'd like to use pi over 2 where it has a nice radius of 10. But what I can use, in fact, is a little bit different. Again, I'm going to divide them all by 3, just like I did before. 0 divided by 3 is 0. Pi over 6 divided by 3, yuck, that's pi over 18. That's not so nice. And pi over 2 divided by 3 is pi over 6. So I'm going to go ahead and just grab that and come over here, and hopefully this can make sense. So 0 is 0. The angle pi over 18, it's about there. This is B, and here is C. So at pi over. Now, one of the nice things is that actually is the first half of that leaf. So what I like to do myself is I just kind of use a little bit of a symmetry argument. Since I know this is half of the leaf, I could go about like that, and that's pretty much what the leaf is going to look like. Now again, as stated before, 2 pi represents the full circle, and there's going to be 3 of those petals because it was an odd number. So the part that's a little bit tricky is this first petal happened at pi over 6. So if I rotated, I'm going to make a common denominator to 4. So 1 pi over 6 plus 4 is going to make 5 pi over 6. That's sitting right over here. And I'll just try to mimic a little bit about the width of each of those pieces so it actually looks okay. So I'm just giving me a call if it doesn't work, okay? And then moving along from 5 pi over 6, let's rotate an extra 4, which is 9 pi over 6, happens to be right down here. Again, just a little bit of extra dots just to kind of help me stay straight. But again, that means this coordinate right here is the angle 5 pi over 6 with a radius of 10 and 3 pi over 2 with a radius of 10 as well. Now, again, I do a little bit better with the odd ones as it turns out. So there we go. So there's pi over 6, there's 5 pi over 6, and there's my 3 pi over 2 coming in for Desmos. Now, the last one, this one I think is always kind of surprises people when they see it for the first time. What about if you just did 2 theta? Now, this is going to be 4 petals, which is kind of interesting. But we're going to take a look at a little bit extra on this one. So when we look at this, let's again go with what I want. And I still would love it if I could get away with just simply using these 3 values where the sign is 0, where the sign is 1/2, or when the sign is full. But what I get to use is going to be affected by that value 2. Everything here is going to get divided by 2. The results are going to leave alone. Again, what's interesting is this is actually being modified, but the sign of pi over 4 is actually still going to be 14. So let's see what happens. 0 gives me 0, no big deal. 7 at pi over 12, which is right here. Here's ABC. 14 by the time I reach pi over 4, which is right here. And again, I'm just going to go ahead and use that symmetry argument. Since this is right where the tip of the petal is, I'm just going to go ahead and rotate to here. I just noticed that that's 1, 2 of these radial lines. So I'm going to go like that. It's a pretty fat petal, what I noticed. So this one has a tip at 14 at the angle pi over 4. And keep in mind, 2 pi is the circle. There's going to be 4 of these things, so it's going to happen every 2 pi over 4. So that means if this is 1 pi over 4, then the next one of those tips is going to happen over here at 3 pi over 4. The next one's going to happen down here at 5 pi over 4. And our last one is going to happen down here at 7 pi over 4. And again, just using that argument, I like to put these little lines in there pointing to them so it can help me count. So 7 was right here, and it went over and back 2. 7's right here in the middle, went over and back 2. And sometimes you get lucky, and there's some things like that that are helpful to make them look a little bit better. And sometimes you don't. So if you don't, it's okay. It's no big deal. But that should do a pretty good job of getting that done. And so that's my graph with all those values, but you'll also see right here, there's 1 pi over 4, there's 3, 5, and 7 in the real graph. By Desmos, looks pretty good. See, these radial lines would come through here. And that's all actually pretty good information. What I was debating about doing is going over some of the symmetry arguments with you in this. And I think that might be worth taking a look at, because one of the things that we know is that when you deal with symmetry, that you can see that this thing does have x-axis symmetry, it has y-axis symmetry, and it has origin symmetry. So I'm just going to go ahead and take you through 2 of those arguments, and then to demonstrate why it has to have all of these things. So for starters, to prove that this thing had y-axis symmetry, one of the ways to do that is to replace r comma theta with a negative r and a negative theta. So if this is my original problem, this is actually a very easy one to prove, because if I replace r with negative r and I replace theta with negative theta, It's really nice because the sign is an odd function, so the negative pops in front, and you're going to notice that the two negatives could cancel each other out, and I got back to the original problem. Forgot to put that 14 in front. And so anyway, we got back to the original problem. That's awesome. So I know that it has y-axis symmetry. And as I mentioned in class, if I can prove one more symmetry, then all three come for free because I don't actually have to earn the third. You cannot have two. If you have one, that's okay. But if the second one fails, then that's all it's going to have. But if the second one succeeds, then the third one's going to come for free. Now, here's where it gets a little bit hard to do, is I'm going to show you origin symmetry. We're going to look at origin. Now, origin has two ways. So one way is if you replace r theta with a negative r and a theta. Now, that's going to be a problem because if I leave theta alone and I replace r with negative r, that's not going to do anything. But that's hard. I can't tell. And so I actually tell students that this is like a false negative. I tried it and it didn't appear to be true. And that's a little hard, but that's one of the reasons why it helps to know what the graph looks like. So we're going to try this one here instead, which is we're going to replace r with r, and we're going to replace theta with theta plus pi. Now here's where we're going to have some hard work. So r became r. The 14 is still there, and I'm going to replace this theta with this. So 2 times this would be 2 theta plus 2 pi. Now, I have to show that this is exactly the same as the original thing. But what's kind of cool is we just ended up with an argument that looks like this. It's the sine of something plus something, which means we've got 14. I've got the sine of the first, 2 theta, times the cosine of the second. There's a plus, so it's plus cosine of the first times the sine of the second. Now that may look like it's an awful lot of work, but it turns out some nice things happen because on the unit circle, the cosine of 2 pi is identically 1. Because remember, that's going all the way around the circle. And the cosine right here at 2 pi is 1. But similarly, because the sine is the y value, remember this is the coordinate 1, 0, so the cosine is 1, the sine is 0. So all you do is simplify ever so slightly. The sine of 2 theta times 1 is sine of 2 theta, and the cosine of 2 theta times 0 is 0. So this entire argument just died, and it's just 14 times the sine, which gave me the original. So again, if I know that I have y-axis and I know that I have origin, it's impossible to have exactly 2 symmetries. So it must, in fact, have the third symmetry. And so that's a quick look at the proof of the symmetry, but you can clearly see that that was true over here, but it explains why it had to be true. So, okay, so I will see you back in class soon. Hopefully that was helpful. We'll do, of course, more of that in class, and feel free to ask for help if you need it. All right, see you back in class.